Download this code from codegive.com, link in the description below. OK, let's dive into backtracking, specifically focusing on the n-queens problem, the m-coloring problem, and sudoku solving. We'll cover the underlying concepts, provide detailed explanations, and include Python code examples for each. Understanding backtracking. Backtracking is a powerful algorithmic technique used for solving problems that can be structured as searching through a state space. It's a form of depth-first search, DFS, where we explore possible solutions incrementally. The core idea is 1. Build a partial solution *. Start by making a choice that takes you to a potential solution state. 2. Check for feasibility. Constraints. Evaluate if the partial solution is still valid according to the problem's constraints. If it violates a constraint, abandon this path, backtrack. 3. Extend the solution *. If the partial solution is feasible, extend it by making another choice. Repeat steps 2 and 3. 4. Reach a solution, or dead end. *. If you've reached a complete solution, all constraints are satisfied, you're done, or you can continue searching for all possible solutions. *. If you can't extend the solution further without violating constraints, backtrack to a previous choice point. 5. Backtrack *. Undo the last choice you made and try a different alternative. This is the key step, you backtrack to explore other possibilities. Key characteristics of backtracking problems *. Constraints *. The problem has rules or constraints that must be satisfied. State space *. The problem can be represented as a tree where each node represents a partial solution. Recursive structure *. Backtracking is naturally implemented using recursion because it involves exploring nested choices. Try and error *. You try possibilities until you find a solution or exhaust all possibilities. 2. The n-queens problem. Problem statement *. Place n chess queens on an n×n chessboard such that no two queens attack each other. This means no two queens can share the same row, column, or diagonal. Backtracking approach *. 1. Represent the board *. We can represent the board as a 1D array queens where queens I stores the column index of the queen placed in row I. For example, queens equals 1, 3, 0, 2 means queen in row 0 is in column 1. Queen in row 1 is in column 3. Queen in row 2 is in column 0. Queen in row 3 is in column 2. 2. Recursive function, solve n-queens util. Base case *. If we've placed n-queens, we've reached the end of the queens array, we've found a solution. Return true. Iterate through columns * for each column in the current row. Place a queen in that column, queens row equals col. Check for safety Is it safe to place a queen in this column? Check for conflicts with previously placed queens. Recursive call If it's safe, recursively call solve n-queens util for the next row. If the recursive call returns true, a solution was found down that path, return true. If the recursive call returns false, a conflict was encountered, undo the choice, remove the queen from that column, queens row equals -1, and try the next column. Backtrack If we've tried all columns in the current row and haven't found a safe spot, return false, we need to backtrack. 3. Safety check, is safe. Iterate through previously placed queens, rows 0 to row 1. Check for column conflict, queens I equals col. Check for diagonal conflict, ABS, queens I, col, equals row I. This checks if the difference in column indices equals the difference in row indices, which indicates a diagonal. Python code asterisk. Explanation asterisk. Asterisk solve n queens, n, this is the main function. It initializes the queens array and the solutions list, then calls the recursive utility function solve n queens util. Asterisk is safe, row, col, this function checks if it's safe to place a queen at, row, col, given the positions of the queens already placed. Asterisk solve n queens util, row, this is the recursive function. It attempts to place a queen in each column of the given row. If it finds a safe column, it recursively calls itself for the next row. If the recursive call returns true, it means a solution has been found. If the recursive call returns false, it means that placement didn't lead to a solution, and we need to backtrack. Asterisk the printboard function visualizes the solution in the chessboard format. 3. The M-coloring problem. Problem statement asterisk. Given a graph represented by an adjacency matrix, or adjacency list, and a number m, the number of colors, assign one of the m colors to each vertex of the graph such that no two adjacent vertices have the same color. Backtracking approach asterisk. 1. Represent the graph and colors asterisk. Asterisk graph, an adjacency matrix, or adjacency list, representing the graph. Graph ij equals 1 if there's an edge between vertices I and j. Asterisk colors, an array where colors I stores the color assigned to vertex I. Asterisk m, the number of available colors. 2. Recursive function, graph coloring util. Asterisk base case asterisk if we've assigned colors to all vertices, we've reached the end of the colors array, we've found a valid coloring. Return true. Asterisk iterate through colors asterisk for each color from 1 to m. Asterisk assign the color to the current vertex, colors v equals color. Asterisk check for safety asterisk is it safe to assign this color to this vertex? Check for conflicts with adjacent vertices. Asterisk recursive call asterisk if it's safe, recursively call graph coloring util for the next vertex. Asterisk if the recursive call returns true, a solution was found down that path, return true. Asterisk if the recursive call returns false, a conflict was encountered, undo the choice, remove the color from that vertex, colors v equals 0, and try the next color. Asterisk backtrack asterisk if we've tried all colors for the current vertex and haven't found a safe color, return false, we need to backtrack. 3. Safety check, is safe. Asterisk iterate through all vertices adjacent to the current vertex v. Asterisk if any adjacent vertex I has the same color as vertex v, return false. Asterisk otherwise, return true. Python code asterisk. Explanation asterisk. Asterisk graph coloring, graph, m, this is the main function. It initializes the colors array and calls the recursive utility function graph coloring util. Asterisk is safe, v, color, this function checks if it's safe to assign the given color to vertex v, considering its neighbors. Asterisk graph coloring util, v, this is the recursive function. It attempts to assign each color to the current vertex v. If it finds a safe color, it recursively calls itself for the next vertex. If the recursive call returns true, a solution is found. If it returns false, it means the coloring didn't work, and we need to backtrack. 4. Sudoku solver. Problem statement asterisk. Solve a 9x9 Sudoku puzzle given a partially filled grid. The grid is filled with digits from 1 to 9, with 0 representing empty cells. The rules of Sudoku are: Asterisk each row must contain the digits 1 to 9 without repetition. Asterisk each column must contain the digits 1 to 9 without repetition. Asterisk each of the 9 3x3 subgrids, boxes, of the grid must contain the digits 1 to 9 without repetition. Backtracking approach asterisk. 1. Represent the sudoku grid asterisk use a 2D array, list of lists, to represent the grid. 2. Recursive function, solve sudoku. Asterisk base case asterisk if all cells are filled, no more zeros, we've solved the sudoku. Return true. Asterisk find an empty cell asterisk find the next empty cell, cell with value 0. Asterisk iterate through possible digits asterisk for each digit from 1 to 9. Asterisk place the digit in the empty cell. Asterisk check for validity asterisk is it valid to place this digit in the cell according to the sudoku rules? Check row, column, and 3x3 box constraints. Asterisk recursive call asterisk if it's valid, recursively call solve sudoku. Asterisk if the recursive call returns true, a solution was found, return true. Asterisk if the recursive call returns false, a conflict was encountered, undo the choice, reset the cell to 0, and try the next digit. Asterisk backtrack asterisk if we've tried all digits for the current cell and haven't found a valid digit, return false, we need to backtrack. 3. Validity check, is valid. Asterisk check row asterisk iterate through the row to see if the digit already exists. Asterisk check column asterisk iterate through the column to see if the digit already exists. Asterisk check 3x3 box asterisk calculate the starting row and column of the 3x3 box the cell belongs to. Iterate through the 3x3 box to see if the digit already exists. Python code asterisk. Explanation asterisk. Asterisk solve sudoku, board, this is the main function. It calls the recursive function solve. Asterisk find empty cell, this function finds the next empty cell, cell with value 0, in the board. Asterisk is valid, number, POS, this function checks if it's valid to place the digit number at the given position POS. Asterisk solve, this is the recursive function. It finds an empty cell, tries each digit from 1 to 9, and recursively calls itself if the digit is valid. If the recursive call returns true, the puzzle is solved. If the recursive call returns false, the digit is reset, and the next digit is tried. Asterisk print board, used to print the sudoku board. Key takeaways for backtracking asterisk. Asterisk identify the choices asterisk clearly define what the choices are at each step of the search, example which column to place a queen, which color to assign to a vertex, which digit to place in a sudoku cell. Asterisk define constraints asterisk formulate the constraints that determine the validity of a partial solution. Asterisk implement the safety check asterisk write a function to efficiently check if a partial solution is valid. Asterisk recursive structure asterisk backtracking is most easily implemented using recursion. The base case is usually when a complete solution is found. Asterisk undo choices, backtracking when a path leads to a dead end, make sure to undo your choices before returning so that the algorithm can explore other possibilities. Backtracking can be computationally expensive for very large problems, but it's a valuable technique when the constraints can significantly prune the search space. Practice with these examples and variations to solidify your understanding. Good luck.